Hi, this is Vipin here. Welcome back to this lecture. So this is the continuation of the part one of this video where we started and discussed the boundary layer description and the equations of boundary layers. So we are going to cover the boundary layer parameters in this video. So these are the parameters which you can see on the screen. So the first parameter being the boundary layer thickness. So what is boundary layer thickness basically? So when the boundary layer formation takes place, so obviously it is having some thickness also, and this thickness is determined by the fact that the velocity of the upper layer of this boundary layer formation is equal to the 99% of the free stream velocity. Okay, so this is the basic condition which we have to meet if we can before we can say that this is the boundary layer thickness of this boundary layer from the leading edge at some given distance x. Okay, so at different distances it is different value because it is a function of this x length. So over the complete length of this it is maximum always. Okay, and it depends whether it is going to be laminar boundary layer or the turbulent boundary layer, or it is falling in the transition zone. So it depends on this Reynolds number. So this is the expression of the boundary layer thickness uh, from the exact solution of the Blasius for the boundary thickness, where 5.0 into x upon under root of Reynolds number for a given distance x. Okay, so x value is variable here, and using this we can find out the boundary layer thickness over the range of x from 0 to the full length of the plate. Okay, so this was about the boundary layer thickness, and this is very simple and basic concept. So there is no need to discussion more about it. So let's move to the displacement thickness now. So when we talk about the displacement thickness, so what is displacement thickness? So displacement thickness is basically, let's suppose this is the phase which you can see A, B, C and D is the phase through which the free stream flow is entering and before touching to the leading edge of this. Okay, so this was the area, but as quick as it is touching the flat plate here, so you can see that the boundary layer formation starts and its thickness is increasing continuously like this. Okay, so when it is increasing continuously like this, so what will happen, whatever mass is entering through this particular phase should be exiting from this also of the same amount, but that does not happen. So what happens, because mass should be conserved here, but because of this boundary layer formation it's not happening. You can see that the area is decreasing here. So to compensate this decreased area, what happens, the free stream of the free surface of the fluid flow just adjust it adjust itself in such a way so that it increases its free surface height by a amount of, let's say, the distance delta star. Okay, so this delta star is nothing but the distance which is called the displacement thickness. Okay, means if mass is just moving from this place to this place, so over the displacement on this flat plate it will be adjusting its height in such a way so that mass should be conserved between these two faces. Okay, and for that there is no other option but to adjust its height, and that is what is done in this case, and this is how it is called the displacement thickness. I hope you understood this, what is displacement thickness. Now let's try to find out what is the expression of displacement thickness. Okay, so let's say this is the width of the flat plate B. Okay, and let's say at some particular region, let me just draw the 2D diagram of it. So this is the boundary layer, this is the velocity profile, and this is the free surface of the boundary layer where the velocity is u infinity. Now let's say there is a location at which it is just u. Okay, it is the small u here. So what would be the velocity of this particular zone? So that would be u naught minus, sorry, u infinity minus u. Okay, so that is going to be the velocity of this, which is the deficit of the velocity and eventually the deficit of the mass flow rate here. So this is the velocity of the mass deficit. So if we talk about the mass deficit in this process, so I can say that mass deficit is equal to density of the fluid into the area. Let's say the area for this thickness is dy here, and since b is the width, so at this particular position, let's say we can consider at this particular position, if this is dy and this, if this is dy and this is b, so this b into dy is going to be the area through which this mass flow rate is exiting. Okay, so rho into this thing, area is b into dy into the velocity of the deficit, so that is u infinity minus u. And if we want to find out the total mass deficit, so we can just integrate it over the range of the boundary layer thickness. So this is how we get the total loss in mass flow rate in this process. Okay, so this is the expression. So this can be written as, rewritten as 0 to delta into rho u infinity minus u b into dy. Okay, now this mass deficit would be equal to the mass flux exiting this particular area. Okay, so this area is having width as b and depth as delta star. Okay, so delta star, so what would be the mass flow rate exiting this particular area? So that is mass flow rate through delta star. So that is equal to uh, mass flow rate through delta star is equal to density is going to be same and area is delta star into b. Okay, so that is the area, so rho into a. And what is the velocity here? So velocity is going to be u infinity. Okay, so rho into delta into b into u infinity, rho delta b and u infinity. So rho delta star b into u infinity. So that mass flow rate would be equal to this mass deficit, and we can equate these equations. Let's say equation number a and equation number b. So I can equate both of these and I can say that rho b delta star into u infinity is equal to uh, 0 to delta, then rho u infinity minus u b into dy. So here b is the width which cannot be changed, and density also, if it is incompressible fluid, so this is also constant. So rho and b are constant on this side and on this side, so I can cancel these. And what I will be having, if I want to rewrite the expression of displacement thickness, so it can be rewritten as 0 to delta here, u infinity minus u upon u infinity into dy, or simply the delta star expression becomes the integration over the range of 0 to delta and 1 minus small u upon u infinity into dy. So this is the expression of displacement thickness. Okay, so this is the expression of displacement thickness. So this will be used for the calculation of displacement thickness, where there is a loss in the mass flow rate over this particular flow process, where the flow was taking place and it was free stream, but suddenly because of the presence of the solid flat plate here, and boundary layer was formed, and this happened, this length distance increased here like this, and because of that we have got this expression. So this is the expression of the displacement thickness. I hope you understood it, and if not, you can just comment in the uh, comment section. I'll try to answer your queries. So thank you. And in the next part of this we will be discussing about the momentum thickness, energy thickness, and shape factor, and if time allows, we'll also cover the skin friction coefficient. So these four parameters of the boundary layer we are going to cover in the next part of this video. Thank you very much and take care.